Okay, welcome back. Happy Tuesday. Under all of those masks, I see your happy, shiny faces. Huh? I just know, it's one of those days. Okay, so last time, in class, what we covered, well, what did we cover? KCL and KVL are going to be a recurring theme. We covered a resistance-only circuit. We are in chapter 2 of the book. Okay. This camera. That's gonna look weird on stream. What else did we cover? We covered a very specific topic related to resistance-only circuits. Anybody remember? I know it's been like 5 days. Huh? We did cover series and parallel, which is an important piece of this. But after we covered series and parallel components, what did we talk about? Equivalent resistance. Okay? And the importance of series and parallel is being able to understand, well, what we're going to be talking about today very much relates to series and parallel circuits, but also understanding equivalent resistance will help us to better understand series and parallel. So they kind of play off of each other. Okay. Did you get a haircut? I've spent this whole time like, who is that? Like, I know you, but I don't know who you are. Did you get a haircut? I feel like you have longer hair usually. Okay, I'm just an idiot then. All right. That happens. With a mask, you only have like this much of your face. Like, can I recognize his eyes? I don't know if I've stared that deeply into them yet. Okay, we're going to keep going. So with equivalent resistance, the concept is that you can take a bunch of resistors and combine them and find one resistor that has the same behavior as a bunch of resistors. It's a way of you know, if you only have a 100 kilo ohm resistor and a 50 kilo ohm resistor, you can turn them into a 150 kilo ohm resistor instead of having to buy a 150 kilo ohm resistor, that kind of thing. Or if you're looking at impedances, you can add them all together. This is kind of a principle that we're going to look at a lot as we build into this course. So what we're going to be talking about in this first hour of lecture, it hurts me to say first hour of lecture. This week we're going to have pretty solid lectures. Try to catch up on what we got behind on last week from the snow day. And building towards next week when I'm hoping to start doing some Raspberry Pi stuff, which I still never did post any of the stuff for the Raspberry Pi, which is awesome. keep getting a reminder to like, make sure to do that, and then I don't. I will do it during the break. I'll post some stuff. In any case, that's what I'm hoping to do next week. Pull out some breadboards, plug some LEDs in, make some lights flash. Okay? Just because that's fun. It's fun to me. And talking about Raspberry Pis is also fun to me. So, okay. So last time that's what we covered. What we're talking about today in this morning class is we're going to cover the concept of the voltage division principle and the current division principle. Now that's just two very fancy ways of saying resistors in series share voltage. Resistors in parallel share current. Okay? So if I have a circuit that I draw, it goes like this. Like that. And we'll say this is 10 volts. We'll go ahead and say that this is 1,000 ohms, 1,000 ohms, and 1,000 ohms. Okay, this will be R1, this will be R2, this will be R3. Okay, and then this is our VS. If this is our circuit, we do not have 10 volts go across every single resistor here. Why? Because then what that means is if you had an electron that were to travel around the circuit, it would go up here, it would lose 10 volts, and then it would go down here, and then it would lose another 10 volts, and it would only gain 10 volts back by going through the battery. Which means once around the loop, it gets a negative 10 volt energy change. That's not accurate. It's unrealistic. It violates the principles of the conservation of energy. Once around the loop, it has to start at 0 and end at 0. So if we arbitrarily say, okay, I'm going to go ahead and ground this end, which means I'm forcing this voltage to be 0, stab a wire into the ground, or into the ground for these, which oftentimes actually just gets connected to the common in a power circuit, but whatever. Stabbing a wire into the ground, it means your voltage here is set to what is commonly accepted in our power systems as 0 volts. Okay, it's not a true 0 volts because voltage turns out to be relative. It's like saying I'm at 0 elevation. Well, that's also relative. Relative to what? Well, it's relative to some location on the sea surface somewhere. That's where 0 elevation is. Well, this is 0 voltage. Why is it 0? Well, it's because that's how we picked it. Two power companies, 0 voltage, may actually have a voltage relative to each other. Just the nature of how it is. You stick a wire in the ground one place, you stick a wire in the ground 3 miles away, the ground voltage might be different. We don't know what the charge distribution is and how it varies. Whole reason why we have lightning is because there's a difference in charge distribution between the sky and the ground. Well, that happens between ground and ground. Voltage, 0 voltage is an arbitrary item that we just say, okay, we're going to call this one 0. Okay? And that's what this is. We're going to call this one 0 volts. Okay? So I'm going to identify this as node 1. This is node 2. This is node 3. This is node 4. We have a loop 1 that goes through the inner resistor. We have a loop 2 that goes through the outer resistor. So we have one that goes in the inner circle, one that goes in the outer circle. Okay, those are our 2 loops that we have. We have 4 nodes, 2 loops. Great. We can play with equivalent resistance and simplify this if we really want to. But I want to, well, yeah, let's go ahead and do that. So 2 resistors in parallel. Does anybody remember what the equation is for equivalent resistance in parallel? REQ equals one over R1 plus 1 over R2. Here it's going to be R2 and R3. Right? That's how we find the equivalent resistance. So if we plug in the numbers here, this is equal to 1 over 1,000 plus 1 over 1,000, which this is 0.001, 0.001. So that you add these two together, this equals 0.002, which means that your REQ1 is equal to 500 ohms. And heck yeah, I did that in my head, Sal. Huh? What now? So math throw down after this. I feel math empowered right now.
I know.
Boy, a way to take the wind out of my sails. I mean, good morning. Just trying to ignore, I'm just trying to use my overlord nature as your teacher to try to belittle you. And you're just like, no, I'm not ready for it. I'll wait till you're ready. It's terrible. Okay, so what we've done here by calculating the equivalent resistance is that we've converted this circuit into a new circuit that looks like this, where this is still node 1, node 2, node 3, node 4. This is still ground. This is R1. This is REQ 1. Okay? All we've done is we took these two, put them into one. And by doing so, that lets us do a little bit of easier math. Because now we have one loop, and that one loop includes, well, it's actually a sum of both L1 and L2. When you combine resistances in series, you remove nodes. When you combine resistances in parallel, you combine loops. So the current going through here is L1 plus L2. Just both of them together. But this is our new circuit. Now, because this is L1 plus L2, that means the total current that goes through R1, as we would see here, both L1 and L2 have to go through R1. Which means that the current that's going through here, before we even started doing any math, we know is going to be current 1 plus current 2. Where this is current 1 and this is current 2. Which means current 1 plus current 2, I mean, the current through here is going to be greater than the current through both of these. Now we can find what that current is by stepping back through the circuit, but we're just playing around with math at this point because who doesn't like doing math in their spare time? Okay, so are these resistors in series or parallel? They're in series. what is the equation for equivalent resistance in series? How do we combine resistances in series? Huh? Just add them. It's here. Whoop. Excuse me. REQ2 is equal to R1 plus REQ1. Just plugging in these two together, combining them to form one common resistance. Okay, here R1 is equal to 1,000 ohms. REQ1 is equal to 500 ohms. So this equals 1,500 ohms. And now what we've done is we've gone ahead and created a brand new circuit that looks like this. This is 4, it is still grounded. This is 1. But we have removed nodes 2. Why did we create a node 3? Node 3 and node 4 can combine. But when we combined these two here, we got rid of node 2. Node 2 is somewhere in the middle of REQ2. Okay? But now that we've done this, we know we have 10 volts. We know that we have a resistance of 1,500 ohms. We can calculate what that current is. Okay? So, how much current is leaving the battery right now? This is still L1 plus L2. How much current is leaving that battery? How do we even calculate that? Huh? We use Ohm's law on REQ2, right? Because we know what the resistance of REQ2 is, and we know what the voltage is across REQ2. So all we have to do is just calculate the current through it. You know 2 components, you can figure out the third. So we know it's 1,500 ohms, we know it's 10 volts. So according to Ohm's law, V REQ2 is equal to I, little I, REQ2 times REQ2. We rearrange this, and what you find is that I REQ2 is equal to V REQ2 divided by REQ2. Okay, it's just rearranging Ohm's law. Once you have this, V REQ2 is 10, REQ2 is 1,500. So 10 divided by 1,500. Huh? I'm trying to do it in my head. That's got to be, it's 0.006.67. No, yes. Yes, he says yes. 0.00667 amps. Okay? So we know that loop 1 plus loop 2, current 1 plus current 2 is equal to 0.00667 amps. Okay? Awesome. Now we can step back through the circuit. We know we have 0.00667 amps of current going through R1 and through REQ1. We know that both of those are the same. Now, if you multiply that, 0.00667 times 1,000 means that this has 6.667 volts running through it. Okay? It's not a full 10. This here has 3.333 volts running through it, or running across it, I should say. So both of these add to 10. Turns out that the ratio 1,000 to 500, because these are in series, the voltage division principle states that the amount of voltage that each has is inversely proportional to its resistance. So, well, it's directly proportional to its resistance. So that means this, having a lower resistance, has a lower voltage across it. Has the same current, and just because of Ohm's law, because it has a lower current, it has a lower voltage. Okay? That's what voltage division principle states, and there are formulas you can come up with it. I'm not even going to write the formulas down because I don't like teaching that way, because I think voltage division principle, and current division principle are more theoretical concepts rather than mathematical principles. I don't want to teach you. This isn't Common Core. I'm not trying to teach you 5 different ways to calculate the same circuit. I've already taught you 2, and I'm going to teach you 2 other ones today. Dang it, it is Common Core. Oh well. Okay. So, yeah. We know that current 1 plus current 2 equals 0.00667, which means you can plug that into here. VR1 is equal to IR1 R1. We know IR1 is equal to 0.00667 because that's what current 1 plus current 2 is equal to. So this is equal to 0.00667, as I said, times 1,000, which means VR1 is equal to 6.67 volts. And you can do the same with VREQ1 is equal to I REQ1 times REQ1, which is equal to 3.33 volts. Okay, so nothing fun, nothing amazing. The voltage splits because these components are in series. That's what voltage division principle is. Now, if we take a step backward and go back to this cycle, we know that between nodes 2 and 3, or 2 and 4, because 3 and 4 are the same, between these 2 nodes, we know that there's 3.33 volts total. Okay? 3.33 volts between nodes 2 and 3 means that there are 3.33 volts between nodes 2 and 3 here, which means there are 3.33 volts across both of these resistors. If we calculate the current that is going through both of those resistors, we know what the voltage is. We know what the resistance is. All we have to do is calculate the current. Okay, so for both of these, they have identical resistances. So they should have the same current flowing through them, right? And if the current here is L1 plus L2, or current 1 plus current 2, is equal to 0.00667, then I would expect that the current flowing through each one of these would just be half of this. So 0.00333 amps. I guess we can do the math. VR2 equals IR2 R2. Fantastic. We know VR2 is equal to 3.33 volts. IR2, and we know that R2 is equal to 1,000. Okay, if you divide 3.33 divided by 1,000, shockingly, you get IR2 is equal to 0.00333 amps. Okay, so voltage division principle. Resistors in series split voltages, but they have the same current. Current division principle. resistors in parallel, split current, but they have the same voltage. Okay, so let me write that out a little bit more explicitly. I'm going to erase this piece of the board. I'm used to writing this out across all of the whiteboards in the room, so bear with me as I very disorganizedly go from one side of the board to the other. Okay, so voltage division principle. Components, I was going to write resistances, but this is true for any components. In series, share, well, no, not share, dang, split. Okay. So if you have resistances that are all in series connected to a battery, then quite frankly, all of those resistors are going to share voltages, and they're all going to sum to whatever the voltage is applied across both ends. And the current division principle, components in parallel split current. And those current values sum to the amount of current that goes into the node going into the parallel components. Okay? All right. So that's that. Let's do a pretty complex example, because I want to build into kind of our next lecture. So I'm going to give everyone a headache real quick. All right, so I'm going to use as much of the board as I possibly can. Bless you. So this over here is Vs. I'm going to say it's 20 volts. Okay. Vs is going to go into a resistor, then going to split into a number of resistors, which will then recombine, come down, and go across this resistance. Back to the battery. Okay, we have this resistor here, and we have these two resistors out here. So, good luck drawing that. I'll go ahead and start labeling every component. This is R1. R2 and R3 are up here on top. R4 is the one on bottom. R5 will be this one. R6 will be this one. R7, R8 over here. We'll make this be R9 and this be R10. I told you I was going to try to... Ha-ha! The purpose of this class is not to entertain you. It's to slowly torture you until you become a zombie. And then you go infect your friends with electrical circuits knowledge. DC power circuit. That's actually what zombies are saying. It's just, they filter it for the movies because nerds. Okay, so first thing I'm going to do is I'm going to start drawing nodes because I want to kind of manage this a little bit. 1, 2, I'm going to go ahead and put a node here. 3, 4, 5, oop, no, bad Cal. This will be 4. Forget, everything that's connected by a wire continuously is one node. So I don't need to put 4 right next to 5. Just kind of muddies up the circuit. 5 will be right here. A section of wire that has no resistances in there. I'm going to put 6 down here. 6 is going to go all over here. That's all going to be 6. Okay? And then over here, this will be 7. And I think I got everything. I'm not going to draw on the loops because I think that would make this super ugly. But what I am going to do is I'm going to create a node voltage table. Okay? If you remember what I was saying at the beginning of class, voltages are arbitrary. You pick a 0 and then you measure everything relative to that in one circuit. So what I'm going to go ahead and do is I'm just going to go ahead and drop down a ground wire here. By doing so, what I am saying is that node 7 is at 0 volts. I could put the ground wire here. By doing that, node 1 will be at 0 volts. Now that said, this increases by 20 volts. That would make, if I put the ground here, that would make 7 be at negative 20 volts. You can do that. It's perfectly valid. You can have negative voltages. I don't like negative voltages because I'm kind of a freak. I like my voltages positive. Be a little optimistic here. Well, stay positive, except for 7, which stay grounded. Okay, so my node voltage table. I have 7 nodes total. 1, 2, 3, 4, 5, 6, and 7. Of all of these, do I know what the voltage value is at any single node? You said 1. Okay, what is the voltage at 1? It's 20. How did you know that? Yeah, that one's a given. A lot of people don't get that the first time I introduced this. Very nice. We know that here, the voltage at node 1 is 20. Why? Because there is a 20 volt increase between node 7 and node 1. That's what the battery does. It takes the electron. This is like in a roller coaster. This is the component that has the lift on it, that lifts you back up 20 feet. Okay? That's what the battery is doing. You start at 0 here, or 0 is where ground level, whatever. Which, by the way, Gabby, I think you were going to say that 7 is at 0. We do know that too, because we grounded 7 You can't solve this circuit unless you pick a voltage value for one of these nodes. And we just pick 0 for 7 by grounding it, okay? Yeah?
Why wouldn't there be another node after R6?
This one? You mean like somewhere up here?
Yeah.
Well, anything that's connected by a wire to 6 can merge with 6 because it's all going to be at the same voltage. You could put other nodes there. I just feel like it muddies it up. You could put like 6, 7, 8, or 6, 6.1, 6.2 at the ends of those if you really wanted to. I don't really want to, but you could. That's perfectly valid, but you'll find that all of the voltages here are going to be equal for those nodes. As long as you remember that, it'll make your math a lot easier. I don't always remember to do that, which means adding more nodes for me just makes it more confusing for me. Here we have 7 different voltage values that we'll find at 7 different locations in our circuit. Okay, now I haven't given you what all the resistance values are. So we're going to make all resistors are 100 ohms. Okay, just to make the math a little simpler. Everything is 100. Okay, we're going to keep this node voltage table on the board because we're going to be filling this out as we go. I want to know what all the voltages are at each node. Okay, and why are we doing it that way? Because what the heck? What does this even mean? Is it crosswise resistor? We only put resistors at right angles. You psycho. Gross. Kiss your mother with those lips. All right, so how do we solve this? Well, all of these, because there's only one power source, all of these can be combined down to a number of resistors in series and parallel. Okay? This is, believe it or not, this is actually a simple circuit. There are some circuits where the resistances do not get pulled down to series and parallel. It's a lot uglier. But this is a simple circuit. So let's go ahead and, before we even do anything, let's try to identify resistors in series and resistors in parallel just in this drawing. Okay? Do we have any resistors in series anywhere? You're saying yes. Name some resistors in series. R7, R8, these are in series. So, series. R7 and R8, R2 and R3. Do we have any other in series?
Can you do like 5 and 10?
They are in series, but the problem is that they go through node 6, and so does all of those. So they're not quite, they are in series, but there are also a bunch of other ones in series too, so it's going to make it hard for us to combine them. We're looking for a 1 and a 1 in either parallel or in series. 5 and 6 are in parallel. We could combine them right away. I'm not going to, just because we know 5, 6, 7, 8, they're all in parallel too. So we're not, well, that was an accident. We're not, We're not going to combine them yet. I'm just going to wait on those. But there are some in parallel that we can combine right now. Right? Maybe? I mean, we could do 5 and 6. I don't want to do 5 and 6 yet. You could combine 5 and 6 right now, that's fine. Are we able to combine R9 with anything? R9 is in parallel with 5, 6, 7, 8, and 10. So, no, not really. Not yet, anyways. We have to get it to a cleaner place, a safer place. All right, so we're going to go ahead and say REQ1 is equal to R7 plus R8. Okay, this is in series, so we can just directly add them. They're both 100, which means that REQ1 is equal to 200 ohms. REQ2, we're going to say, is equal to 2 and 3. Both of them are 100, so we can just add them. The equivalent resistance of 2 and 3 together is equal to 200 ohms. Aight. So now we can redraw this circuit so that it looks like this. Could have combined 5 and 6. Where this here is REQ1, this is R6, R5, R9, R10, R4, REQ2, and R1. When you combine resistances in series, you lose a node. Here we lost node 3, we lost node 5. So now we're not going to know what the voltage is on those anymore. May they forever rest in peace. Okay. Now we connected everything in series, which means in this one, we should be able to then clear out parallels, right? So you do series one configuration, you do parallels in the next configuration, you do series in the next configuration, you do parallels in the next configuration. You just keep doing that over and over again. Eventually you should get to one resistance. Right? Thank you. I appreciate the yes man nature. Yes. All right, so parallel. What resistors are in parallel that we can combine right now? 5, 6, 7, 8. Okay. R5, R6, REQ1. What else? Wish I could dance. 4 in REQ, this is 2. Yeah, because I did it backwards. I put the, yeah, makes no sense. What even is organization anymore? R4, REQ2. Do we have any others in parallel that we can combine nicely right now? Oh, heck no. All right. Oh, I forgot to label my nodes. 2, there's no 3 anymore. This is 4, 5 is gone, 6, and 7. 7 is still grounded. Okay. All right, so our parallel equations, we're going to say REQ3 is equal to 1 divided by 1 over R5 plus 1 over R6 plus 1 over REQ1. Okay? This is 100, this is 100. So this ends up being equal to 1 over 100, plus 1 over 100, It's 1 over 200. So 1 over 100, this is equal to 1 divided by 0.01 plus 0.01 plus 0.005, which means that this is 1 over 0.025, which ends up equaling 40. Nice. Stayed in the board. So REQ3 is 40 ohms. I like it when we come out to an even number. I love it when a plan comes together. Dun, 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 dun. All right, REQ4 is equal to 1 divided by 1 over R4 plus 1 over REQ2, which is, this is 100, this is 200, which means this is 1 over 0.01 plus 0.005, which means it's 1 over 0.015, which I believe is 66.7 ohms, and my beautiful plan is falling apart. Have to have a decimal. Friggin' decimals. Oh, gosh! Okay, so now we've created a brand new circuit. Again, where we combine these two, we combine those three, and we can go ahead and redraw it. Why am I redrawing it? I don't know. I love math, and I love art, apparently. So this is R1, REQ4, REQ3, R9, R10. Oh, gross. I can label my nodes again. This is node 1. This is node 2. This over here is node 4. This down here is node 6. This down here is node 7, which is still grounded. Our circuit's getting smaller. We're getting closer to the source. We are figuring out the math. Eventually, we're going to get to the source. We're going to find out how much current is coming out of the battery. To the point where we all break into a rousing round of how great math is. Gabby, you want to lead it? Oh, all right. Huh? Oh, where's the can-do attitude you all came in with this morning? Dang it! That was the moment when I absorbed your souls. Okay. Let's keep going. Do we have any resistors in series here that we can combine nicely? 1 and 4. That 1. So series R1 and REQ4. Do we have any other resistances in series that combine nicely? 3 and 10, right? Because they both one output that's shared between both of them, that makes them in series. One single node with only 2 resistors connected to it. One resistor is input, one resistor is output. They're in series. Okay? So REQ3 and R10. All right, so just adding them in series. REQ3 is 40 ohms. So we'll say REQ5 is equal to R1 plus REQ4. REQ4 is 66.7 ohms. R1 is 100 ohms. So REQ5 is equal to 166.7 ohms. Meanwhile, REQ6 is equal to REQ3 plus R10. This one's equal to 100 ohms. This one is equal to 40 ohms. So this is equal to 140 ohms. Now we can draw a new resistance circuit that looks like this. So this is REQ5, this is REQ6, and this is R9. Well, that's gross. I'm gonna go ahead and, yeah.
So you put R9 and REQ6 in parallel now?
Yes. Nice work. I drew it like this just to try to confuse people. But that's good seeing. So this is node 1. We lost node 2 when we combined R1 and REQ4, which means we now have node 4 over here. Node 4 is connected to R9, this series, and that series. The only other node we have is 7, which we know is connected to ground. We've gotten rid of every other node. I did that off camera. I try to do my dance moves in a place where I won't regret sending them on the internet. This isn't TikTok, this is YouTube. Ugh. Okay, as Dylan pointed out, these two have the same input and output nodes. These are in parallel. I could redraw this very easily where it's resistance up top, resistance here, resistance here. You can do that. Those are exactly the same circuits. Just because it's put at a 45-degree angle doesn't change anything. It just means it's at a 45-degree angle in the drawing because that's how I wanted it to fit. It doesn't make the behavior any different. It's a normal resistor. I just drew it at an angle. So these two are the same. This is just slightly more compact. Okay? Which is nice because I'm very quickly running out of board space. So, here we started by combining resistors in series. Here, then we combined resistors in parallel. Here, we then went back and combined resistors in series. Here, we're going to combine resistors in parallel. And then the very last step, we're going to combine resistors in series again. And be done. It was madness. No, wrong. And then we're going to step back through the circuit and do all of the math that we left out. So, yeah, I lied to you. Okay, so the two resistors in parallel here are R9 and REQ6. So REQ7 is equal to 1 divided by 1 over R9 plus 1 over REQ6. Which R9 is 100 and REQ6 is 140. Okay, I'm not doing that in my head. Just not you, Sal, okay? I just pretend. You know what? Fake it till you make it, right? 58.32?
33.
58.33?
Yes.
All right. I will blindly take your word for it because I don't want to have to do the math myself. Okay, so now that's the only thing that we can really combine because this is in series with both of these in parallel. But now we have one circuit that has REQ 5 and REQ 7 in it. Node 1, node 4, node 7. Okay, the equivalent resistance here is just going to be, because these are in series, so both of them added together. So REQ 8 is equal to REQ 5 plus REQ 7, which is equal to 158.33 ohms. Dang it, no it's not. This is 166.7. Ugh, math. You gotta do me dirty. Gross. Okay. So, my bad. This is actually 225. All right. So our final circuit is node 1, node 7. This is still grounded. This is REQ 8, and it is equal to 225 ohms. All right, we're halfway done. Okay, so now 225 ohms, 20 volts. It means that the current coming out of the battery, I source, is equal to 10 divided by 225, because that, if we do Ohm's law on REQ8, V REQ8 is equal to I REQ8 times REQ8. I REQ8 is equal to I source. It's just Kirchhoff's current law in that little loop, which means that IS is equal to 0.0444 amps. Okay? All right. So that is true for everything. REQ5. Well, now as we're looking at it, can we figure out what VREQ5 is? If we know what I source is, can we figure out what VREQ5 is? Huh? It's not 20 because 20 has to be shared here between REQ5 and REQ7. So 20 is between 1 and 7. 4 has to be at some voltage between 0 and 20. You can use the voltage division principle to look at the relative difference between those two resistances. That is one way of solving it. I don't like solving it that way. The way that I like solving it is we solve for IS, which means we know what the current is going from node 7 to node 1 in every circuit. Goes all the way back to here. The current from 7 to 1 is 0.0444 amps in every circuit, okay? We know that to be true. So, since we know the current here, do we know the current here? Henrique says yes. You're Henrique, right? Okay. Good. I'm not going crazy. Sometimes I just shout out random names. And I did pronounce that right, yes? It's a good way to start out a Tuesday. We know what the current is going through here because we have one loop. One loop means our current is equal in every component, which means we can find what VREQ5 is because we know what the current is and we know what the resistance is. We have that third component, voltage, that we can just solve for. So VREQ5 is equal to IREQ5 times REQ5. IREQ5 is 0.04444444444444444. And REQ5 is 166.7. Okay. So, doing some quick maths. VREQ5 is equal to, I ran out of board space. Friggin' dang it. I'm just going to start writing these numbers over here off camera while reading them on camera. So we know VREQ5 is equal to IREQ5 times REQ5. IREQ5 is equal to 0.0444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444444. And REQ5 is equal to 166.7 ohms. Multiply them together, you get 7.4074 volts. Oops. So 7.4074. If we do the same with REQ7, REQ7, well, that's not right. I did something wrong.
We have to start from REQ8 and then
You calculate the current, right? Because you know what the voltage is across REQ8. You calculate what the current is through REQ8. The current going out of REQ8 is equal to the current coming out of the source. Current coming out of the source, calculated at 0.0444, which now I am questioning. I 0.0. Yeah. You said that, Solomon. I got it wrong by a factor of 2. This is 0.0888889. Okay, which would make this be 14 point. Times 14.81481 volts. Okay, that's right. Okay, now what we know is that the voltage across REQ5 is 14.814814 volts. Okay. Do we know what the voltage is at node 4? We can find it, right? We know the voltage at 1 is 20. Does it then decrease or increase by 14.81? Are we going to 34.814 volts? Are we going down to 5.185 repeating? Which one? Subtracting, right? We end up at 5. So an electron coming up through the battery starts at 0, gains 20 volts, loses 14.81481 volts, and then across here that means it should lose 5.185185 repeating, right? Right? Well, if we take 0.08888889 and multiply it by REQ7, we should get 5.185 repeating, right? Right? Why don't we do that? Just to check our math. REQ7 is 58.3 repeating. Multiply it by it, you get 5.185 repeating. So we did something right. And that means node 4, the voltage is 5.185 repeating. Yes. Math. Okay, so now we know node voltage at 4, which means we could find the current through R9. We can find the current through REQ6. We can. That's not too bad. I don't want to find the current through 9 because that's not going to help us at all. We can find the current through REQ5, but we already know that. It's 0.0888. Because if you do KCL at node 1 over here, it's 0.0888. It has to be equal to the source voltage. So, plus we already know what the node voltage is at 4. Let's go ahead and find the current through REQ6. Okay? So, REQ6 is equal to 140 ohms. Okay, and what's the voltage across REQ6? It's the voltage between 4 and 7, right? Node 4, node 7. What's the voltage difference between node 4 and node 7? 5.185, right? Because it's going between 0 and 5.185. So that's what the voltage is across REQ6. We can now calculate what the current is across REQ6 because we know what that voltage is. Okay? Quick maths. With REQ6 being 140 ohms, and we have, so 5.185 divided by 140 means that the current going from 4 to 7 through this branch is equal to 0.03737 repeating amps. 0.037 amps. All right, which means that the rest of that 0.0888 repeating goes through R9. That's all that means. I don't want to calculate that because I don't care about R9. I'm just trying to find the node voltages. Okay? So now that I know that the branch going from 4 to 7 is 0.037 amps, we know we have 0.037 amps that goes from 4 to 7 through node 6. We're just stepping back through the system. So we have 0.037 amps going through there. Having 0.037 amps flowing through that part of the circuit means we can multiply 0.037 by REQ3 or R10 to find what node voltage 6 is. Okay, which one would you rather do, REQ3 or R10? Do REQ3? All right, we'll do it. So REQ3 is 40 ohms. So 40 times 0.037. Repeating. 40 times, which means that there is a VREQ3 is equal to 1.48, 148 repeating volts. Okay? Now, what does that mean that the voltage at 6 is 1.48, 148 volts? And I just write that in here. There's a collective glaze in this classroom. Don't worry, we're going to take a break right after this. So I just calculated VREQ3. I plugged in the current going through REQ3 times what REQ3 is, and I get 1.48, 148. Do I just write 148, 148 right here at 6? Is that what the node voltage is? That's the voltage here between 4 and 6. Which means that's not the voltage between 6 and 7. It's the voltage between 4 and 6. So if I actually want to do it, that is the voltage drop from 4 to 6. I have to subtract 1.48, 148 from 5.185. So that means that node voltage 6 is 3.7037 03, 07, 03, repeating. I need to start erasing part of this board. Okay, and we can keep doing that. We now know what the voltage is between 4 and 6. Okay, we know what the voltage is between 2 and 4. We can calculate what these individual currents are, we can calculate what those currents are, and then we can step back through here, okay? So I'm going to spend my break finishing this table, and I'll show you what the table is after break. But go ahead and take a break and rest your brains. I will see you back here at 9:30.